All right, welcome to this session. It's going to be about architecting for continuous delivery. My name is Jakob. I work for a company called Active Solution here in Stockholm. We're developing cloud solutions for our customers, and we have a booth outside, so please visit us during the breaks and talk more about this stuff or anything else, or test our cool games as well. I'm a Microsoft MVP. You probably know me from hits such as continuous delivery using VSTS. My blog, very, very popular, and tweets. So kidding aside, please contact me outside and talk more about this stuff because it's something that I'm really interested in. So continuous delivery, this is one of the definitions that I like. The ability to get changes into production safely, quickly, and in a sustainable way. What it doesn't necessarily mean is that you have to deploy 10 or 20 or 50 times every day. That's not the end goal of continuous delivery. It's more like you should be able to, at any given point in time, release a new version of your application. Because if we can do that, if we can have a team, a process, or tooling that allows us to do that, we can move this to be a business decision. So it's more to the business to decide, should we deliver every day, every other week? It's more of a business decision. And this is kind of the end goal of continuous delivery, because not all applications has to be delivered 50 times per day. So let's start off by setting some principles for continuous delivery. First of all, we need, of course, to have a deployment process that is, repeatable, reliable, does the same thing every time. And by that follows really the second point. We have to have automation in place. As soon as we start adding manual steps along the way, it will be error prone, we will be dependent on specific people and so on. And that is something we want to avoid, really. And if something is, painful along this process, these manual steps or anything, try to do it more often. We often help customers, moving from maybe releasing every 3 months to, dragging it down to every 2 weeks. And then you find out that some of these steps that you actually could do before, because you released so seldom, you can't do that anymore. You have to, for example, add automation if you want to release on a faster cadence. So keep everything in source control. Probably, obvious for all developers here that we keep our application code in source control. But this also goes for the environment definitions. So for example, if you're using Azure, you're using ARM templates that describe the environment, so we can build, test, and deploy also the environment, not just the application itself. And also keep them in version control together with the rest of the application. We also need to shift the focus a bit. We as developers tend to think that my feature is done when I'm done with the code and I've written a few unit tests and I've checked everything in, the build is screen. But we need to think further ahead really, and think that our feature isn't done until it's built, tested, deployed into production, and used by our end users, and we're actually getting telemetry data back. Because that is actually when we can analyze it and see, okay, is this feature actually being used in the way that we thought it would? That by then we're done, and this really means that we have to think more about having cross-functional teams really, because you have not just developers and testers on the team. You also need stakeholders, you need operations and so on, because you need to cover the entire line all the way to production here. And everybody on the team should be responsible for this whole release process. Because if you don't know how it works, you're kind of shying away and you're just pushing code and hope that it will work in production some magical way. So you need to think about this in the same way as you do with the rest of the system. Everybody should know how this stuff works and should be confident enough to actually change in the deployment process, and to know how is this stuff deployed, how is it monitored, and so on. That's really important. So looking at a few kind of architectural things that stops us, and also process related things that is stopping us from doing continuous delivery. First of all, often when I talk to customers, I find that they have this application that started out pretty in a simple way. Most applications start out simple. It's a kind of web application, maybe some web API, a database, and it works just fine. And then they start adding, new features. They add more developers and start, pumping more code through this application. It just grows and grows and grows. And, somewhere along the way, it becomes this tangled mess of, tight relationships, tight dependencies that you can't really strip apart anymore. And now this become what usually is referred to as a monolith. It's kind of a monolithic application. It's just one big lump of code. that is very hard to tear apart, and it's actually hard to deliver this application continuously in a fast cadence if you have this. So this is a major problem. Usually you also get stuck in using legacy technology due to this, because it's hard to, in a big application, lots of code, lots of dependencies, it's hard to say that, okay, we need to change the framework we're using, we need to upgrade Angular to the latest something. That decision becomes pretty hard, it takes a lot of time, it takes investments, so you just, maybe next sprint, so you just keep pushing that further away. So now you're sitting with old technology that you have to have skills for that, and also sometimes you're stopped for using kind of modern tooling for deployment and so on if you're stuck with these legacy things. So that's also a problem. Typically, there's also like a huge single code base with hundreds of thousands of lines of code. So, when I as a developer come into this project, it's just overwhelming to see this code. It's really hard to understand how this works. And it typically often results in developers starting creating branches instead. That tends to be a bit long-lived because they're kind of afraid to change in this huge code base. So instead they create a branch and they work in isolation, and then we stop doing continuous integration because I work in isolation. And also when I work in branches, we tend to not do as much refactoring as we should, because we don't really know what the other guys are doing in the master branch. So I just add my features all along the way. So this is also a bit of a problem as far as continuous delivery is concerned. Also, they tend to have large batch sizes, and by that I mean that every release going out tends to have a lot of changes, a lot of code churn. And that is effective. If you release seldomly, you want to release as much as possible. And this is also a problem because it's really hard to deliver a lot of new functionality without adding new problems to the product. So you're going to introduce new bugs. The deployment itself will probably be more unstable because it's so much changes going out. So we actually need to reduce these batch sizes. And generally, all this stuff just results in teams doing these big bang releases, which is usually done outside working hours because it takes so much time. The system will have some downtime. So you have you're doing during the night or during the weekends. Maybe you have a service window every month for 2 hours where you're allowed to take the system down. So it becomes this huge uncomfortable things that nobody really likes. So we really want to move away from this. So let's look at a few kind of enablers, a few things that we can think about to move towards continuous delivery. And the first thing we need to do is to break up this monolith. We have to tear this stuff apart into smaller pieces, because by doing that we can change these smaller pieces and deliver them independently of each other, and by that just will create more stable releases. Second, when we do this, when we split this application apart into lots of smaller moving parts, we have even more of a distributed system than we had before. And we need to think about resilience here, and this goes in general for distributed systems, but also when we add the continuous delivery, when we deliver more often, we have to make sure that the system actually handles this. It has to handle that dependent service that I talk to will eventually be down. There will be downtime, and I can't assume that the rest of the system is up when I deploy my service. So we need to make the system resilient and kind of self-healing to handle these cases. And finally, I'm going to talk a bit about keeping the application releasable at all times. So as I said in the beginning, we should strive for being able to deploy application at any given point in time. So we have to avoid doing this like large breaking changes, these huge commits or pull requests. We have to reduce the batch size here and work in smaller steps where each step is releasable. That is the key point here. So how can we make this kind of breaking changes in smaller steps? So I'm going to talk a bit about that. But first of all, breaking up the monolith. So kind of the traditional application can look something like this, where we have this kind of a layered architecture. We have the UI, we have the service layer and domain layer, and then we have this database, typically SQL Server in our world, at the bottom that the application talks to. And there's nothing inherently wrong with this architecture. This is a good architecture. It's just that it doesn't scale. That is the main problem here. So when it does scale, when it does grow bigger and bigger, we get these tight couplings. Also, it's very, very common that the database in the bottom is just this common integration layer, really. Nobody means to do this, but it's so easy because all the table just lies there. It's so easy for me to just join them in, So one part of the system writes to a table, and then you have another part that reads from the same table. And now we have this annoying dependency. And often we have instead 20 or 50 parts that reads from this table. They join it and so on. And that creates a dependency that it makes it hard to change that table because it affects so many parts, and it's really hard to tell which parts are affected by this. So it becomes this common integration layer, and that's a big problem. A database is in particular SQL Server, is often like the elephant in the room when it comes to continuous delivery. It's hard to do it, especially if you have this kind of architecture. And typically then everything is deployed together in a big bang release. So we just take the system down, build everything, test everything, and deploy everything, just because it's so connected together. And I mean, this is a problem that we talked about for years in this industry, and component-based architecture really was a way to trying to solve at least some of these problems. So we take the application and we break it apart into what we call components, because then we can at least we can build them, we can test them separately, and then we can assemble them somehow. So that solves some of the problems, but we still have this problem with typically binary dependencies here. We still have to assemble the right version of all these components and package it up to an application. And often we end up in this, the Newton soft problem where everybody relies on some library that some team are building. So we get this version hell, we get this dependency from some framework team that needs to, deliver new stuff on this common code. So that is still a problem. So it doesn't really go all the way. So the last couple of years, the concept of microservice architecture has become really popular. And it really goes hand in hand, I would say, with the DevOps culture and then the cloud becoming more and more popular, where it's now much easier to, deploy a lot of stuff compared to what it was like before, where we did everything on premise. Now we can spin off new stuff very, very easily. So this goes really hand in hand. So now we take one step further and consider each part basically its own application. So every service here is running in its own own process. You can consider it to be an application really. So it could be running on the same host as the other services. It could be running on different hosts, and the same service could be scaled out to multiple hosts. And each microservice now is internally it could be like this layered architecture, for example, if it fits. And it has its own data store now. So, we have split this huge database up into smaller pieces. And now every microservice can select the type of data store that is the most appropriate for that case. So it doesn't have to be SQL Server anymore. So maybe one has SQL Server, the other one is using Redis for like kind of in-memory thing. The next one is using MongoDB, for example. So, pick the technology that fits the best. So a few principles. I stole this from Sam Newman's book about microservices, which is really good. So some core principles here. Typically, microservices are modeled around the business domain. And this is a really important part, because when you start splitting up your application, where do you cut it? And if you cut it wrong, you're going to end up having probably more problems than you had before, because now you have distributed dependencies, which actually is worse than having in-process dependencies. So it's really important to find the right boundaries here, and this goes hand in hand really with domain-driven design and the concept of bounded context, which I will talk a bit about more later. They should have a separate code base. So now we don't have this one big code base. Instead, each microservice has its own code base, which tends to be a lot smaller. So it's easier for me as a developer to understand it. It's easier to change. It's easier to actually rewrite it if I would have to get away from the legacy tech and so on. They're also decentralized. And this is also, I was touching upon that earlier, because traditionally we maybe as architects have tried to set up this, architectural guidelines that every part of the system should follow. And we have every good intention to do that, but as we all know, things change. So at the start of the project, some principles might apply, but 1 year from now or 2 years from now, we have no idea what it's going to be like. So it's really hard to have these guidelines that everybody should follow and have it successfully. So here instead we're thinking decentralized, move those decisions away from some kind of central governance, and instead have each team decide what is the best architecture for my service or our service. What is the best tooling? What is the best and so on. And so this could be very different now. We can have one architecture in one service and complete another architecture in another service, and so on. And that is also the way that we actually can move faster forward, because now we can pick the best tooling and so on that the teams are comfortable with. Automated, of course. I mean, before we had maybe one big application. Now we have 10, 15, 20 microservices. So it's kind of obvious that we have to have automation in place to be able to build, test, and deploy all these things. And now they're also deployed independently. And this doesn't just mean that we have to have the deployment pipeline for every microservice so we can build and deploy them. But it also means that we can't assume too much about the rest of the system. If I need to deploy my service, I can't assume that all the other services had also been updated to a certain version, because I can't tell. This is a distributed system. I don't want to have these coordinated releases, because then again we're having dependencies that we have to wait for other teams. So I should be able to deploy a new version of my service without having all the other services break due to some not backward compatible change. So we have to think compatibility here. That is a really important point. And as I mentioned before, it should be cross-functional teams where we have all these skills, both for developing, testing, QA, monitoring, and so on, inside a team, and also from the business side, so knows that part of the domain. So this could look like something like this, where we have a bunch of microservices running in their own hosted process somewhere. They have their own data store, and it could be a SQL Server, Redis, MongoDB, and so on. And then we have maybe applications on the outside that talks to these microservices, so web apps, API gateways, and so on. So, talking about the bounded context, and if you're familiar with domain-driven design, you probably have heard this concept before, and it's really about taking a large, complex business domain and splitting it down into more manageable parts that is easier to reason about. And what you're going to find when you do this is that you're going to see that there are often a few concepts that occur in several contexts. So in this case, from Martin Fowler, we have the sales context, so that's basically the sales department, and then we have the support context, which is the support department. And both of these departments, they refer to customers and products, as is described in this model. And but they're probably not referring to them in the same way. They don't need to store the same information about the customer. They might not even call it the same thing. That is something that we have to find out when we do this domain modeling and talk to the people that work there. But this really goes hand in hand, because this has turned out to be if we get these boundaries right for our microservices, they tend to be the most stable ones. And we want to have as loose coupling as possible between these things. So if we try to follow the bounded context pattern and domain-driven design, that is a really good start when you're looking at breaking your application up in smaller pieces here. So also then when we do this breaking up, we end up with more integration points than we did before. So before maybe we had a lot of in-process function calls. Now we have distributed out-of-process calls, REST calls or queues or whatever it has. And there are some guidelines we should follow here when we're talking about the integration here. So first of all, loose coupling, that's something, loose coupling is always good, of course. But there is a tension between coupling and complexity here that I will touch upon a bit later. You should also follow something that's generally referred to as smart endpoints and dumb pipes. And this really comes from the SOA world, the service-oriented architecture, which is, in a way, it's a bit similar to microservices. But what generally often happened in the SOA world, we tend to use this concept of enterprise service buses that generally was some kind of middleware product that we either built ourselves or that we bought. And this thing in the middle became like a huge beast that everybody depended on. And it did too much. It didn't just send messages between the services. It also applied model transformation and used business logic to enhance models and so on. So too much logic ended up in the middle here, and that is something that we want to avoid here. So the concept here is that you put the smarts, the logic should be inside the endpoints, that is inside your services, and the communication between should be as dumb as possible. So simple REST calls, simple message queuing, and that kind of regular stuff in between, and put the logic inside the microservices, because that is where they belong, not in some service bus. also then when we do microservices, many processes that we implement actually spans over multiple microservices. So we have to call multiple microservices somehow to actually implement a lot of processes here. And there is this, here is a bit the same thing about the coupling here. We need to find a way to do this with as low coupling as possible. So there's something called choreography over orchestration that I will talk about for a guideline here. And in the end, the dry principle, this is kind of interesting because, dry, don't repeat yourself. This is something that we have been taught from day one as developers, that duplicating code is a bad thing. We don't do that. But the thing about not duplicating code, if you don't want to do that, okay, then we create some kind of shared code base. And we distribute it using NuGet or, Git submodules or whatever. Somehow we share this common code. But now we have a dependency. Which is bad, that we just talked about for many reasons. So here is also a trade-off. You don't want to have too much duplicated code, but if you try to share it instead, then you will be stopped, because then you have this team building this framework that every other takes a dependency on, and then you have to wait for that team, and you have to coordinate releases with that team, and so on and so on. So relax a bit about this dry principle, specifically when it comes to domain-related code. You can, of course, still have these like extension methods for string manipulations and so on. Those should be, tucked away in a NuGet library. But otherwise, keep the domain-related code should be in each microservice, and it's okay to have a bit of duplicated code because it gives you a lot of advantages in other areas here where we're splitting aside. So, as I said, coupling, we really have a tension here between coupling and complexity. So the easiest way, of course, is to have service A call service B. That's the easy thing to do, but it also gives us the highest coupling. Now A is tightly coupled to the B service here, of course. And if we go down the scale of complexity, the best solution here, so to speak, is more of an event-based solution where instead A publishes an event and B subscribes to this event. So now A and B doesn't know about each other at all. So there's no coupling between them. So very loose coupling. But on the other hand, this is of course a more complex solution to build. But in the end, most solutions that are successful in a microservice world tends to use this, because not only does it give low coupling, it also scales so much better than when you're doing straight calls like this. So really try to strive towards loose coupling and look for this event-based mechanism to distribute what's going on in the system, and also a way to distribute data between services. So an example of this orchestration and choreography. So in this case, we have, for example, handling a new customer coming into the system. So when that happens, we need to do a few things. We need to create some kind of points balance. We need to send him a welcome pack using the post service, and we need to send him a welcome email. So the most obvious way to do this is using what's called orchestration. I basically just create a customer service which knows what this process should look like. So it, first it calls the loyalty service, then it calls the post service, and then it calls the email service. And this is very easy to implement, and it's easy to understand. But we have a very high coupling here, and also generally it ends up with the customer server has all logic here. So it turns into this God service, as we like to call them. And the other services probably are pretty dumb now. They don't do much. They just receive a few calls. So there's no logic in it. And also, if you want to change this process, we always have to go inside and change the customer service. So if we're turning this around and use what is known as the choreography approach, and this is the event-based approach with the lower coupling. Instead, we have the customer service just publishes an event that contains the information about this new customer. And then the other services can just subscribe to this event and do whatever is necessary by that point in time. So now there's no coupling between these services. The logic will be much more evenly distributed, and I can easily add new services along the way to subscribe to the same event here. So this is event-based architecture. There's nothing new about it, but you need to think about the things when you start pulling things aside. How should we communicate here, and strive towards loose coupling all the way. So if you're thinking about moving to microservices architecture, it generally doesn't take a sprint or two. It's more like a year or two or something, depending on the size of your application. So this could be a really large project. And I've yet to see a successful big bang rewrite project. where you just say, okay, let's stop everything and just, build this completely new architecture from the ground up. And a year later, everybody's happy. That's never happened as far as I know. So you need to find a really way to gradually move towards this kind of architecture, if that is what you're looking for. And one pattern you can use here is called the strangler application pattern. And the general idea here is that, okay, so let's start by building new functionality in the system as microservices completely on the side of the existing application with their own data store and everything, and keep the existing application as it is. And then what you do there, if you can see it, there you add kind of a dispatcher thing on the top, which basically is kind of a routing thing that just accepts incoming requests and then decide, okay, is this part of the new service? Then we route it to the new service. Otherwise, we route it to the original application. So this could be basically, for example, a web application, and we could start by maybe adding a recommendation feature to the web app. This could be implemented separately in a microservice. So all web requests coming in, the UI router can just check, okay, is this part of the recommendation? Then I will just route all the way to the microservice instead. Otherwise, I will route to the original application. And then we can keep adding new microservices on the side here. And hopefully in the end, we will have a lot of microservices that kind of covers this old application, so it strangles it. That is the reason for the name, and hopefully we can eventually get rid of this application then and just have these microservices. And this process could take years, but then you can at least deliver value along those years instead of doing this big bang rewrite. Okay, so next part, design for resilience. There's a great book called Release It. I can really recommend it, where he talks a lot about how to build, stable and resilient system that actually works in production. And he talks a lot about the integration points being the kind of the number one killers for systems, for distributed systems. And it's like in the real world when you build constructions, when you mold things together. So the weakest part is really when you attach the different constructions elements. And it's the same thing in distributed software. The weakest parts here are really the integration points. So sure, you will still have bugs internally in your code sometimes, but generally when you're looking at problems in production, it's where your services are integrated with each other. That's where the problems turn out. So you need to be kind of skeptical when you're building distributed systems. You have to assume that errors will happen, due to network latency, traffic spikes, or the application being deployed at any given point in time. You can't assume anything. More like you should assume that error will happen and deal with it. So there are a few patterns that I want to talk about here that is very common in the distributed systems world. And it's really related to continuous delivery, because if we want to deliver often, we can't have a system that goes down every time we deliver. So that is kind of the point of having it here. So the first obvious kind of pattern here is wait and retry. And it's really simple. So let's say I have a service that calls another service and I get an error back. Okay, so depending on the error here, depending on what kind of error we have here, I could select to, wait for a while and try again. And because it might be a transient error that will actually, you have a problem now right now, but maybe in 2 or 5 seconds, it will be okay. So if I still get a kind of 500 error back, I could select to wait a bit longer, just to kind of an exponential wait here, and try again. And yay, it works. So in this case, we had a kind of a transient error. Maybe the server responded with 503, server too busy, because at the moment it was having a lot of requests coming in. Or maybe the service was just being updated, so we had a bit of downtime. Those kind of errors is really good for this retry thing. But it doesn't apply to all cases, of course. If you get an access denied back, there's no point, in doing retries. And you also have to make sure that these operations that you're retrying actually are idempotent. So you actually can call them multiple times here, because you can't really be sure. If you call the first service here, let's say it's place order, and then it times out. Okay, should I call it again? Should I call place order one more time? Well, if I do, I have to make sure on the other side that the system handles this and doesn't, place a duplicate order here. So that's also important. But this can solve a lot of scenarios and make the system a bit more resilient and a bit self-healing in the sense that it actually will come back alive again. What it can cause, though, is that if you're doing a lot of retries, you can actually also create more problems for the system, because if you're calling a service that already has problems, it's being overloaded by requests, and then you call it and say you get an error back. Okay, let's retry. And if the entire system is doing this, then the other service will have even more problems. You will create an even more unstable solution here. So there's a pattern called circuit breaker that is intended to solve this problem by not just doing retries all the time. So it kind of simulates a real life circuit switch here. By first the switch is closed, so the traffic can go through. If we detect problems, we open the switch and intercept every call. So it could look like this. We're calling a service, and then we notice some problem. And typically it's not just one problem here, because if we get one error back, it's not enough to say that, okay, this service is obviously unstable. So, but maybe if we get 5 or 10 errors during a certain period of time, that could be enough to say, okay, probably the service now is having problem. Let's open the switch here and intercept all the calls that comes in. So now we will respond back quickly to the client code and say, okay, we're having a problem now. So it will not experience timeouts and those things. But also the point now is that the service 2 will have more resources available to actually handle the problems that it has instead of our just pumping through requests all the time. But then we can still again you can retry after a certain amount of time, and maybe we're still having problems, so we keep on doing this until eventually the call will go through. And configuring these things, configuring how long should the timeout be, what should the threshold be, that is hard, and there's no fixed guidelines here. But this is a really, really good pattern. It's used in a lot of distributed systems around the world. So check that out and try to implement a variant of this. So basically, this is proxies that intercepts all your outgoing calls to services. And finally, Bulkhead Isolation is another pattern that is very, you're using it today, but you maybe don't know that it's called the Bulkhead Isolation pattern. So bulkheads is these things that when you build a ship, you create sections in the hull, so that if the ship would hit an iceberg, you would take in water, but at least the water won't flow through the entire ship and sink it. So the ship will still operate, but with reduced capacity. And you should think about the same way when you build your system, that if you have error somewhere, you should try to isolate that error and not having it spread all over the system and take everything down. So you want to partition your resources in some way, and there's several ways to do this. So one easy way, one simple way that you might be using already today is that you can partition, for example, by client. So in this case, I have maybe a big web shop with a lot of traffic, and then I also have a mobile version. So it could be a separate mobile site or a mobile app. And these applications have different, varying kinds of traffic. So what we could do here to handle this case, that we could basically just deploy, in this case we have a payment service cluster of some kind. So we deploy basically 2 instances of this cluster that the web application and the mobile application talks to. So if we see a lot of traffic from the mobile site, we will have problems on that cluster, but the web application will still work. So this is just one way of partitioning your resources in a way that you want to isolate the problem as much as possible. And where you should partition it, that's really up to your system, and you have to analyze where could things probably go wrong. But then at least we can, some parts of the system might go down, but the rest of the system actually works and still provides, business value. So there's a great open source library called Poly, if you're doing .NET development, that implements a lot of these policies for retry, circuit breaker, and so on. So take a look at that. So I just included a very simple example here, what it can look like if I'm calling some service and I configure it now. So if I get a web exception back, then I want to apply wait and retry. So basically I want to retry 5 times, and between every retry I want to wait for a specific amount of seconds. This is just one way of configuring it. So check it out, because it's a nice library and a lot of activity there. So last part, keeping your application releasable. The goal here, really is to have, the team works on the same branch, or committing to the same branch regularly. and every commit going into the master branch should be shippable. That is the end goal here. And there's a lot to it, and I will talk of a few things here that is important then. So first of all, as I talked before, work in small batches. We have to, we can't make large changes all the time because there's no way to enforce the quality of those large changes going in and being able to test them. So work in smaller changes all the time. And more importantly, these changes then must be compatible. And this is really important, and I was talking about before when we deploy services independent of each other. We can't assume anything. So every change we do need to be both forwards compatible and backwards compatible. And that includes like service endpoints, message contracts, database schema, and so on. All these things need to be changed in a way that we can always deploy this change. And it's not even up to us when this will be deployed. It should be the business side. I say now it should be deployed because now we have customer demand, and the stuff lying there in the master branch should be deployable. But we also need a way to hide new functionality until it's finished, because we're going to commit code, and I might be midway through my feature and it's not being done. So we need a way to hide that features, which we'll be using feature flags for. So when we're doing this kind of, we have to do breaking changes sometimes. So we need to find a way to just do this in a gradual way. So we can use this expand contract kind of pattern. Which is really simple. So basically you start off by expanding your interface or your schema. So you add new stuff to it, because this is a safe operation. We can always add new stuff that doesn't break anything. Then we need to migrate. So we have a migrate phase in between. So we need to migrate the consumers or the clients of this functionality from the old functionality to the new functionality. And this could take a while, depending on what kind of change it is. And eventually, when everything has been migrated to the new functionality, we can contract, we can remove the old code or the old database column or whatever it is. So it could look like this. We have a customer service with 3 methods, and I don't really like and we have a lot of clients using these methods, and I'm not really fond of this design, so I want to add a query pattern here instead that would replace those 3 methods, and I want to deprecate the old ones. So then we can start by so the first thing is the expand phase. So I add a new method, and I just mark the old ones as deprecated, and this change can then go into production because it doesn't affect anyone. The clients will now actually be notified that the old methods are now deprecated, so that means I should move. So then we have the migrate phase, which is when the clients should be switching from the old to the new methods. And as I said, this could take a while, depending on how many clients do we have, who is in charge of actually changing those clients. It might not even be us, it might be third-party clients and so on. But eventually, all clients will have been migrated to the new system or the new function, and we can use monitoring in production to make sure that nobody's using the old endpoints. So finally, we can contract it and remove the old code, because we don't want to have old code lying around. So we need to make sure that we actually remove this stuff when it's done. And the same thing can apply to database schemas. So let's walk through an example here. Let's say I want to rename a column. This is the kind of refactoring that is seldom done because people are really afraid to change the database. Mostly because they don't have a clue about the dependencies, who is actually using it, so it feels annoying. So they just, they keep the old name lying around just because it's so much work to change it. So in this case, I have a table. I have 2 columns, first name and last name, and I have some code that reads first name and writes last name. But I want to rename last name to surname instead for some reason. Maybe that's the name that in my domain language is using. So the first step then, the expand phase, would then be to add a new column. So we expand the table by adding a new column with the right name and just mark it as nullable because it doesn't have any value yet. Then I change the code. So the code that reads the property or the column will now first try to see, okay, is there a value in the new column? If not, then if it is, it will return that value. If not, it will return the old value. And when I update the column, I will actually update both columns here. And this change can also go out in production. So now we have 2 columns living side by side for a while. But that is just fine because all existing clients will still work. And then we have the migrate phase, and it's a bit special than in database case, because now we actually have a data migration to do. So in this case, it's very simple. I just need to copy data from last name to surname. But this, this process can potentially be complex and involves, transformations and so on. But basically, it's about copying data from the old one to the new one, and I just have to make sure that I don't overwrite anything that's actually being written to the new column now. But that is a problem that I can handle. And eventually, when everything is done, I can remove the old column, mark it as not nullable, and change back the code. So the point here is really that all these steps maybe went on for a couple of weeks, but I could deploy this stuff to production all the time, and nothing broke. So it was a breaking change, but I split it up in small parts. That is really the goal of all types of changes, and it requires a bit of a mindset to always work like this, to not just change everything and push it and hope that it will be deployed without problems. So always think, compatibility. And this also goes for the messages that we send around the services, the schemas. So we need to think, and schemas are a bit special message, because we have kind of a two-way dependency here. We have clients and we have servers, and the client creates the message and sends to the server who reads the message. So both parts are dependent on this schema here. So we have to think, backwards compatibility. If we change the schema, the same thing again. We have to, think about the default values and so on. So those changes are still backwards compatible. But we also need to think about forward compatibility. So when I read the schema here, I should not assume too much about the schema. If I have a schema with 50 properties and I only use 4 properties, I should only read those 4 properties. I shouldn't just deserialize the entire schema, which is a very common thing to do in .NET. You just create a class that deserializes the entire schema. But then I have a tight, dependency to all the properties. For example, if we're using XML, if I instead using XPath and just, select the 4 properties that I use, then the other stuff can change. So I'm much more forward compatible if I apply that kind of pattern. So the service can actually remove fields that are no longer being used, and I don't care because I'm not reading that field. So this is known as a tolerant reader pattern. So, don't assume anything. Be as tolerant as possible when you're reading stuff from the message schemas. That will give you a lot more opportunity. And finally, sometimes you need to do these large-scale changes anyway. Let's say that we're talking to some external payment service for doing credit card payments, and we're actually, we're partnering up with this new firm that has a much better service, so we need to switch to that one instead. That is a big thing, and we can't, gradually, we can't have some calls going to the old one and some calls going to the new one. We have to flip, it's either the old one or the new one. So how do we do this then? Well, then we can apply something it's called branch by abstraction. It's kind of a weird name, but it's instead of branching and changing a lot of stuff, we add an abstraction between. Sometimes you already have this abstraction in place if your design is good from the beginning. But otherwise, let's add an interface in between and implement that for the existing service and deploy this into production. And once that is done, then we can start implementing the same abstraction but for the new interface. And this we can do, in parallel and deploy this to production all the time. Because the existing application is just, using the existing service here. And once we're done, we can swap to the new payment service and, remove it from the. So this is also a way to, do kind of larger changes to applications, but still being able to deploy continuously during that time. And finally, about the unfinished features, we're going to deploy, changes all the time to production, but my feature won't be done. Maybe it takes several weeks if it's a big feature, but I still should be able to commit my code. So by doing that, we use feature flags or feature toggles, and which is basically it's a glorified if statement. If this feature is enabled, run the code. If not, don't run it. So this is a very common way to hide unfinished features, and it's an alternative to branching. Instead, we're using the same branch, but we're hiding stuff in if statements, and we can continue to deploy this code. And this can also add the effects then that we're when you're using feature flags, we're actually can now separate this concept of deployment and release, which is actually two different things. Deployment is deploying new bits into production. But release, that's actually part of enabling this feature for the user. And that doesn't have to be the same thing. Usually when you're deploying stuff without feature flags, it goes straight into, and the user sees it and start using it. And that also, so this actually causes or enables us to do a lower risk deployments, because now we can deploy and make sure that the deployment works. And then, later on, we flip the switch and the users now start to use the new feature. So at least now we know that the deployment is okay. So now we might have problems with the functionality, but at least we have separated those two steps. So that actually makes for lower risk deployments. And also feature flags enables a few more things. We can do A/B testing, for example. We can have a feature flag that gives 50% of the users can see one login page, but the other 50% can see another login page. So we can do this A/B testing and compare what happens when we do it. We can do canary releases, so we can deploy the new version of our system to a specific set of users. So maybe we have some pilot customers that always get the new version first. And if everything okay, we can flip the flag for the rest of the users. If it's not okay, we can turn off the feature flag, fix the problem, and deploy again. So feature flags gives us a lot of possibilities. But they're also kind of a technical depth. So you need to make sure that if you're adding this code, these if statements, you don't want them having them lying around in your code base to make sure that you're removing them when the feature is deployed into production. And also make sure that the feature flags are on as high level as possible, preferably on like the API surface or in the UI. And as far as UI is concerned, if you're making small changes to UI, you can cover that part in feature flags. If you're making larger changes to UI, it's usually a better idea to create a separate UI, create a new page instead that is deployed in parallel with the existing page, because it can be hard to make a lot of changes in the UI and have parts of it being hidden by a feature flag. It can be a bit hairy sometimes. So in that case, just create a new web page with a new functionality side by side, and have the UI router use the feature flag to route to the correct page. So just to summarize then, enablers for continuous delivery, breaking up your system into smaller pieces that will allow you to deliver new stuff faster with less problems. You should design your system to be resilient, to be self-healing, so we can actually deploy stuff all the time. And you're going to have a more distributed system, so you have to think more about these concepts if you have a traditional kind of a monolithic application today. And there are ways, to keep the application releasable. Sometimes it's called as a trunk-based development, where the whole team is working on the same branch. So you need to find a way to accept changes that always can be released into production. And I talked about some of them today. So that's it. I think I'm out of time, so I'm going to stick around here. We have lunch break now, so if you have questions, just come out here or come to the Active Solution booth afterwards and talk to me about this stuff. Thank you.